Hello everyone, welcome to another video. Today we will be looking after hexadecimal conversion. So we will understand how we convert values from binary to hexadecimal, hexadecimal to binary, hexadecimal to denary, denary to hexadecimal. So before we start, I would like to do a basic recap. We must know that hexadecimal has a base 16, meaning it has 16 unique characters. So it can contain characters from 0 to 9 and A to F, giving us a total value of 4, 5, 6, 7, 8, 9. This is in total 10 characters. A, B, C, D, E, F, giving us total unique character is equals to 16. So what are the applications of hexadecimal number system? Well, if I had to give you just two applications where hex is used, one would be used to represent color codes. So if you use Adobe Photoshop or Canva, you could see color codes in this format. Right? Each of the two characters represent one of the colors R, G, and B. So it's used in color code. Another application which we will study in the syllabus itself is in IPv6. We'll study this in networking chapter. So yeah, this is the application. Now let's start with the conversion. Now before conversion, I would like you to recognize a pattern. You see, if you count the position of the number, right, you can see if you start from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So F lies in the 15th position. And what is the highest value or numerical value that a 4-bit binary number can represent, a nibble can represent? So the highest value must have all ones. This equates to 8, 4, 2, and 1, which is, if we sum 8 plus 4, 12 plus 3, 15. So a consistent or repeated 1 in a nibble corresponds to 15 in hexadecimal value, and we cannot move further than this. So there is no sensible value of a 16 decimal number, right? So we always split the binary number into many parts of 4-bit, and we calculate the hexadecimal value. So it's kind of a BCD application. We split them into 4 repetitive bit, and we take out the value and write it in this form. So how do we do this? So for instance, there is a binary number with the value this, right? It's a 8 bit binary number. Now we need to convert it into hexadecimal. So what we do is split the byte into 2 parts, since it's a byte, right? So we make we make divisions from 4 bits. So 1, 2, 3, 4, one division, 1, 2, 3, 4, another division, and we calculate the value. So 1, 2, 8, 1, 4, 8. 8 plus 2 plus 1 is 11, right? 8 plus 4 plus 1 is 13. Now, what is 13? So if this is 15, this is 14, this is 13. So 13 is D, and 11 is B. So BD is the hexadecimal equivalence of this byte, right? Now in a similar manner, if I had to convert a value of F3, a hexadecimal value of F3 into a binary equivalent, the number would be, so what's the corresponding position of F? It's 15. And what's the corresponding position of 3? Well, we need to calculate the binary value. So what equals to the binary value of 15? It's 1, 1, 1, 1. 8 plus 4 plus 2 plus 1 is equals to 15. What's the binary value of 3? Well, 1 plus 2 is 3, rest are 0. So this is how we convert from hexadecimal to binary. Now if we need to convert from hexadecimal to denary, you just do the same process, right? You convert it into the similar pattern which we follow. So F3 corresponds to, so this is 0, sorry, this is 1, this is 2, no 4, no 8, this is 16, this is 32, this is 64, this is 128. You sum them all and get a value which corresponds to denary number. Now if we had to go the other way around, the rule is again simple. If we have a 33 denary value, what's the binary equivalent of 33? Well, we definitely need a 32 here. We don't need 16, we don't need 8, we don't need 4, we don't need 2, we need 1. So 1, 2, 3, 4, 5, 6, 7, 8, right? And what do we have here? We separate it into 4-bit system. This is equivalent to 2, this is equivalent to 1, this is 2, 1 in by a hexadecimal number system. So this is how the conversion is done. Remember to use BCD whenever you're working with binary number system, because in BCD we split the bits into 4 parts. Similarly, we split the bits into 4 parts in order to convert the value into hexadecimal, because 15 is the highest number of value a hexadecimal value can take. There is also another step to convert the hexadecimal value into denary number system. So if we have, let's say, 21 and we need to, sorry, 33, and we need to convert it into no, not 33. 33 is a binary number. Okay, if I had 21 and I had to convert it into, let's say, directly into denary number system, 2 into 16 plus 1 into 16. And once again, as it was with the binary number system, we keep on adding the power according to the position. So 1 is in 0th position, 2 is in 1st position. So 2 times 16 is 32, plus 1 times 16 to the power 0 is 1, gives us 33. Now if the number is small, this method works well, but if numbers get atrociously large, it's not feasible. For instance, 16 times 4 times 7, how are we going to calculate this? It becomes very tough, as calculators are not allowed in paper 1. So this step works really well for the binary calculation. Okay, this is all about the hexadecimal calculation. See you in the next video. Bye bye.